Okay, a question came up. We wanted to do another problem with Lagrange multipliers. Now, turns out the problem wasn't so much with Lagrange multipliers as with solving the simultaneous equations, but let's move on. So, your function is xy, and you are constraining it with the ellipse x squared over a squared plus y squared over b squared equals 1. That is, you're just looking at f of xy values for xy coordinates on this ellipse. And this is, of course, can represent any ellipse centered at 0, 0. Okay, well, then we observe that the ellipse is a level curve of the form g of xy equals c, where g of xy equals x squared over a squared plus y squared over b squared, and c equals 1. That's a level curve of this function for c equals 1. It follows, by all the arguments we used previously, that the tangent to the level curve, in order not to be, for the function not to be increasing or decreasing at a point, the tangent to your level curve at that point has to be perpendicular to the direction of maximum increase of the function. Okay, so on this curve, the direction of the tangent has to be normal or perpendicular to the direction of the gradient of this function. Gradient being the direction of maximum increase. If we move perpendicular to the direction of maximum increase, we have a zero rate of change, which is a condition for an extremum, for a maximum or a minimum. Okay, well, so it follows then that in the first place, a perpendicular to level curve of this function is just equal to the gradient of that function at the given point. Okay, because the gradient, well, okay, again, it's the geometry of the level curve indicates, it shows that moving along the level curve is perpendicular to moving in the direction of maximum increase of the constraint function. Okay, so that means that we have an extremum if the gradient of the function that we're evaluating is parallel to the gradient of the constraint curve. Okay, so to say two vectors are parallel, say one is a multiple of the other, we choose to write that as gradient of f is a multiple of the gradient of g, del g, and the constant is lambda. And that's going to be true for some lambda, and we need to determine lambda. Okay, well, in this case then, gradient of f and gradient of g are easily calculated, so here they are. Gradient of f, then, the condition that the gradient of f be a multiple of gradient g, multiple being lambda, tells us that this expression is equal to lambda times this expression. And it's very clear then that the I components being equal give us this equation, the j components being equal give us this equation. And we're also constrained to be on the level curve. That is, we also have the constraint here. So this is 1, 2, 3 equations in 3 unknowns, x, y, and lambda. Okay, well, there are many ways we can approach solving these 3 equations. The way I chose is we're going to solve the first and second equations for lambda, and then we're going to set those two equal. So all I've done is I've solved this for lambda, I've solved this one for lambda, and I've set those two expressions equal. And then I've simplified what I have, and I get y squared equals b squared over a squared times x squared in a very straightforward manner. And then we plug that into our constraint equation. In other words, we've written down this equals this. We've solved it for y. Actually, we solved it for y squared. No reason to solve it for y yet. And then we're going to plug that into this equation. And conveniently, this equation has a y squared. So things don't always work out that nicely, but we just replace y squared then with b squared over a squared times x squared here. And simplify. And we're led very quickly to the conclusion that x has to be Well, that x squared is equal to a squared over 2, comes immediately out of this, so that x is plus or minus the square root of a squared over 2. Okay? Square root of a squared over 2 is either a or negative a, depending whether a is positive. Presumably for an ellipse it would be positive, but it doesn't have to be. In any case, we get x equals plus or minus square root of 2 over 2 times a, and that solution should follow in an obvious manner from this equation. Then, what's y? Well, we just saw that y squared is b squared over a squared times x squared. X squared is a squared over 2. So y squared is b squared over a squared times x squared. And since x squared is a squared over 2, that's going to be b squared times a squared, b squared over a squared times a squared over 2, just b squared over 2. So many ways we can get this. We can substitute this in here and get it 2. But it's very easy and straightforward to see that this is the case, so that y has to be plus or minus square root of 2 over 2b. Now there's a nice symmetry in these solutions, as you might expect, because of the symmetry of the ellipse with respect to the x-axis and with respect to the y-axis. Okay, well, we now have solved for x and y, so we can find what our values of lambda might be. Lambda, from the first equation, a squared over 2 times y over x. Well, what's y over x? Well, y is plus or minus square root of 2 over 2b, x plus or minus square root of 2 over 2a. It doesn't take a lot to determine that y over x is going to be plus or minus b over a. So if we use the plus here and the plus here, this divided by this x divided by y, is just a over b. It's y divided by x, b over a. Okay? And then if we use a plus from here and a minus from here, or vice versa, opposite signs, we get negative b over a. Those are the only possible values of y over x. So that lambda, which is a squared over 2 times y over x, has to be a squared over 2 times either plus or minus b over a, and that's going to give us plus or minus 1/2 ab. Well, that's pretty much it. We could go to the second equation, though, just to see if we're consistent, and we find that if we do the x over y, it's going to be plus or minus a over b, and we're going to end up with exactly the same expression. Okay? So, there are our solutions for lambda, x, and y. Well, next thing we want to do is we're going to graph the ellipse and graph the position of those solutions, and then see if everything makes sense. There's still quite a bit more to do to determine whether we have extrema. One other thing we did here is we did take our solutions for x, y, and lambda and plug them in to this. And you can see what we got. Lambda is plus or minus 1/2 AB. So it's kind of written sloppily, but there it is. Okay? The 2 is the 2. The x is equal to plus or minus square root of 2 over 2 times a. And of course the denominator is a squared. So we have an a here and an a here and an a squared here. So that all goes away. We have a 2 times 1/2. And then we have a square root of plus or minus square root of 2 over 2. 2 times 1/2, well, that just gives us 1. Square root of 2 over 2 remains to match the square root of 2 over 2 on this side. All the a's and b's except one b divide out, so that this equation that we get when we substitute the values of x, y, and lambda is consistent. It turns out to be true. So we're pretty well convinced that we have good solutions.